gosh, this thing is already green. Not a good sign. Okay, basically, I want to start by reviewing a constrained variational problem. And the idea is to consider an energy function like this, or functional like this, which is a weighted integral of the first derivative squared plus the function itself squared. And we want it to be normalized with respect to a certain weight function. You might wonder, why do we have a weight function? Well, imagine that you were doing a problem in 3 dimensions, like the hydrogen atom. Then your integral here might be from 0 to infinity dr, the square of the wave function, but this would be 4 pi r squared for the radial wave function. So that's the reason, or one of the reasons why one has a weight function. And if we want to find the minimum, we want to minimize the energy, and but while respecting the normalization condition, then we use Lagrange's multiplier technique and define a function of u, the function, and lambda, a parameter, and we write it this way. And so then, I think we've already been through this. We consider small variations in u, and what we find out is that the function that minimizes the energy subject to the normalization condition is one that satisfies this equation together with natural boundary conditions, at least if we require that the energy be stationary with respect to arbitrary small changes in the function u. If we rewrite that slightly, we can see that it actually looks like this, namely that there's a self-adjoint differential operator which, acting on u, gives us an eigenvalue lambda. So Lagrange's parameter is turned into an eigenvalue. The weight function shows up here, and there's the function. So this is a Sturm-Liouville problem, and lambda is the eigenvalue. Now, last time we talked about how this lambda can be thought of. By the way, we're considering functions here, u or u and v, that make the boundary terms vanish. Those are the functions in the domain. They have to be twice differentiable and so forth. It turns out that if we know that the Sturm-Liouville equation, the eigenvalue equation, if we multiply by u and then integrate, we get this, which is that, and then integrating by parts and dropping the surface term, which for functions u in the domain automatically vanishes, we wind up with simply the energy functional. So this eigenvalue turns out to be a ratio of the energy functional to the normalization condition. And now we can think more broadly here, namely, we can see what's going on. Namely, we've got a quantity which we can call R of u, R for ratio, of the energy to the normalization condition. A function that minimizes it is the function that satisfies the Sturm-Liouville equation with the eigenvalue we were looking at here, the one you find automatically, which is the lowest eigenvalue of this ratio. But then you can say, well, what about other eigenvalues to this Sturm-Liouville equation? Well, those turn out to be ones that will minimize this ratio for functions u that are orthogonal to the eigenvalue, I'm sorry, the eigenfunction that actually minimized, that minimized the ratio. So in other words, the one that most minimizes the ratio we'll call the first eigenfunction u1, and the lowest eigenvalue then is lambda 1. Then we can say, well, what about minimizing this with respect to functions that are orthogonal to the first, the eigenfunction that minimizes it? Well, that will give us an eigenfunction u2 and an eigenvalue lambda 2, which will be greater than lambda 1 necessarily. We can continue in this way. We get a sequence of eigenvalues and eigenfunctions. And what is kind of intuitively evident, and which is illustrated immediately by these examples, for example, for the square well potential, the eigenvalues are of this form, n pi h bar squared over the width of the well, b minus a, plus b. And so you can see that as n goes to infinity, these eigenvalues go to infinity. That's an important property of the eigenvalues of these self-adjoint Sturm-Liouville systems. And it's important mathematically and physically. We see the same thing for the harmonic oscillator, namely the well, let's see, where's the equation for the eigenvalues? Well, I'll write it down. The equation for the eigenvalues is that lambda n, say, is h bar omega n plus a half. This is the famous harmonic oscillator, set of harmonic oscillator eigenfunctions. And, oh boy. All right, let me call Tom. I mean, this is really outrageous. Tom, the screen went green as you left, and moreover, it turned off a few moments ago, and now it came back green again. So this system is not working.
This is the new one that I just checked because I found the old one. So,
yeah, well, the new one sucks as badly as the old one.
No, it's odd because when I checked it earlier, it worked perfectly. So
it's an intermittent problem. It's an intermittent problem, a bad connection. The connectors don't fit perfectly, and so they intermittently fail.
Okay.
Although it may be that the failure is due to something in the classroom hardware itself, and not.
Yeah, I checked it out exactly that same hardware. So anyway, I'll check it again.
All right. Thanks. Bye. Okay. So all right. Now we've got nothing at all. So. By the way, I originally thought that this new building would be a disaster. Turns out that because of some architectural flourishes, I thought for about a week that maybe I was wrong, but now I'm pretty well convinced the new building is a disaster. So let's get rid of this stupid screen, and instead I'll try to just lecture normally. So, as I said, the harmonic oscillator eigenvalues do go to infinity. Another example is Bessel's system. So for Bessel's system, the energy functional is an integral 0 to 1, x u prime squared of x plus n squared over x u squared of x dx. N of u is an integral 0 to 1 x u squared of x dx. And the eigenvalues, well, it turns out that the parameter n is not an eigenvalue. Instead, it characterizes the Sturm-Liouville equation. The eigenvalues will be lambda nm. And it turns out that one can show, and I'm here quoting Courant and Hilbert, that the limit as m goes to infinity of this is 1. So in other words, lambda n, the mth eigenvalue of the nth system, goes as m squared pi squared for large m. So what we see is that these eigenvalues go to infinity, at least in these examples, and I'll show you in a few minutes an argument that that this is a general feature of Sturm-Liouville systems. We can consider, if we want, complex eigenfunctions, but it turns out that that is more of an illusion than something that's mathematically real. If we do consider a complex solution of this equation, remember P and Q and rho are real. These will always want the Wronskian of psi, say, alpha and psi alpha prime and psi alpha star between A, B. We want that to vanish. Those are the boundary conditions. And it follows then that you have the inner product of chi with chi L psi, which is an integral of chi star L psi dx. Because this is the functions, are eigenfunctions of the differential operator, which is a self-adjoint system. This is from A to B. This is the same thing as A to B. L chi star psi dx, which we could rewrite as L chi psi. So these are the sort of relations one sees in quantum mechanics, and in particular we can go through a quick set of steps that are analogous to those that you probably have seen in a quantum mechanics class when there was a discussion of eigenfunctions of Hermitian operators, or eigenvectors of Hermitian matrices, namely that they, the eigenvalues are real, and that when the eigenvalues are different, the eigenvectors are orthogonal. The analogous relations here are, we've got L psi I is lambda I rho psi I, L psi j is lambda j rho psi j, and so then we can say psi star JL psi I is psi J star lambda I rho psi I, and psi I L psi J star is psi I lambda J star rho psi J star. So if you subtract this from that and integrate, what you find is that 0 is the integral from A to B of psi J star L psi I minus L psi J star psi I dx. And now, using the right-hand sides, what we get is lambda I minus lambda J star times an integral A to B of psi J star rho psi I dx. So what does this tell us? If we set J equal to I, then this says that the imaginary part of the ith eigenvalue times this is equal to 0. In other words, it's the equation 0 equals lambda I minus lambda I star integral AB psi I star rho psi I dx. If that is equal to 0, well, rho is a positive weight function. This is psi, the absolute value of psi squared. So I can rewrite this as times, so that thing on the right-hand side is clearly positive, and so since the product of that with this is 0, that means that lambda I minus lambda I star has to vanish. That means that the eigenvalues are real, so the lambda I are real. Once we know that they're real, we can then go back to this equation where we have 0 equals that, and we can get rid of the complex conjugation because it doesn't matter. And then what we see is that if the eigenvalues are different, we can divide through by their difference, and we get that the functions, the eigenfunctions for different eigenvalues are orthogonal when integrated with respect to the weight function rho. So that is what we're seeing here in the Sturm-Liouville context is a recapitulation of what you've probably seen in the quantum mechanics class for finite dimensional emission matrices and their eigenvectors. In any event, that's something that I went through in chapter 1 on linear algebra when we discussed Hermitian matrices. So you may wonder what's going on here. If psi I might have would have an imaginary, in other words, psi I would be ui plus I vi. You might say, gee, we've got two real functions as eigenvalues. In fact, what we could do, since we have this equation, and since L is real, if we just, so let me take this equation and replace J by I. And now complex conjugate this equation. We know the lambdas are real, we know rho is real, we know L is real because it's just a derivative, and P and Q are real. So we get this equation. So then adding the two together, and subtracting the 2 and dividing by I, we get that if psi I is ui plus I vi, the real part and the imaginary part separately are eigenfunctions of the Sturm-Liouville equation with the same eigenvalue. On the other hand, the subtle thing here is that these, we would then be saying that ui and vi are both solutions of a second-order differential equation that satisfies the boundary conditions. There are 2 boundary conditions. That means that either ui and vi don't satisfy the boundary conditions, or if they did satisfy the boundary conditions, they'd have to be the same function. And because, after all, if you have a solution of a second-order differential equation and you have it satisfying 2 boundary conditions, then it's unique. So you can't have 2 different solutions. So then you may remember that I said that if we had one solution of a self-adjoint differential operator or equation, we could use Wronski's method to find a second solution. Namely, it would be d prime dx prime over p of x prime y1 squared of x prime. And so you might say, well, this is a second solution. It is a second solution, but it doesn't satisfy the boundary conditions. And an example, let's see, do I have a, well, we'll see examples later. For the moment, let's look at another property of these Sturm-Liouville systems. In particular, what we're going to see is that if f of x is a function in the domain, so in other words, it's suitably differentiable and satisfies the boundary conditions, then we can write this as a sum of coefficients times eigenfunctions. And this is, so basically any suitably differentiable function, any function in the domain, in other words, we're satisfying the boundary conditions, and it's, I forget, is it once differentiable continuously or is it twice differentiable? Anyway, suitably smooth function f of x, we'll see that we'll be able to write it this way, expand it this way in terms of the eigenfunctions, and we'll have convergence in the mean, which means that f of x minus sum I equals 1 to n of ai ui of x, absolute value squared, rho of x dx, that this will go to 0 as we take the limit of n going to infinity. So this is called convergence in the mean, and we also know that these eigenfunctions are orthogonal. That was one of the things that we showed on the blackboard that's covered. Let's see, I think it was, well, it was here somewhere. Anyway, it was a consequence of this equation that we can divide through by this when the eigenvalues are different and the functions are orthogonal when integrated with respect to the weight function. So, that orthogonality means that if we integrate f of x, in other words, we're writing f of x like this, we integrate f of x with respect to rho of x and a particular eigen value eigenfunction ui of x dx, or let us say uj. Then we substitute for f of x. This is a sum ai ui of x, rho of x, uj of x, dx. These guys are orthogonal when integrated with respect to rho, and the ai's are constant, and so this is the sum ai delta ij, which gives us aj. So the coefficients aj are given by integrals like this. And if we use this formula for the a's and substitute into here, what we get is that f of x is the sum I equals 1 to infinity ui of x times ai, but ai is the integral of, let us change the variable from x to y, rho of y, uj of y, dy. So that's what we get. Now, if we rewrite that slightly, we can say this says that f of x is an integral, and I guess we're always talking about an interval from a to b, and then we have f of y, and multiplying f of y will be a sum. What was my variable? J? Oh, I think I UI, AI, this should be an I. And so this is the sum, I equals 1 to infinity, ui of x, rho of y, uj of y. Let me get rid of this. It's distracting. So we have this equation, but of course we can compare this with the delta function equation. So in other words, what we find is that these eigenfunctions provide a representation for the delta function of the form ui of x, rho y, uj of y. And since this sum is non-zero only for x equal to y, we don't really, we could have rho of x as well as rho of y, and in fact what we could do is even call this a sum I equals 1 to infinity. In fact, the rho isn't even in the sum. So what we could do is say it's rho of x to the power alpha, rho of y to the power 1 minus alpha, times the sum on I of ui of x, uj of y. So the eigenfunctions of these Sturm-Liouville functions, equations, give us delta functions. And the delta function itself, if we trace all this backwards, what we get is the delta function lets us write the function f this way. If we do the y integration, we get then the coefficients I'm a little confused as to why there's an I there. Yeah, this is supposed to be an I. What we see is that this is ui of x times the integral of f rho uj. That's ai. So that gives us back this sum, or this representation of the function. So the delta function relation tells you can expand the function, any function in the domain D, in terms of the eigenfunctions of the Sturm-Liouville equation. Now this is, well, let me get to the unboundedness of the eigenfunctions, of the eigenvalues. This is just kind of obvious, and these eigenvalues are the stationary points of this ratio, and this, on the other hand, is p u prime squared plus q u squared dx over integral rho u squared dx. And the reason why these eigenvalues eventually go to infinity is that if you have an eigenvalue, an eigenfunction that has a nice shape like that, you can just add some jitter and make the jitter higher and higher in frequency, and then that means that the u prime squared term will get bigger and bigger, and since p is a positive function, that goes to infinity. And an example is the figure 7.2, and what I now realize is that I should have computed what the energy was in that case. I just said it was intuitively clear that it goes to infinity, but it would not be very hard to, well, if it goes to infinity, I guess there's no way I can, for a finite number, I could compute it, but it goes to infinity. So this is something that we've seen with the eigenvalues of the square wave potential, the harmonic oscillator potential, Bessel's potential. You might say, well, what about the hydrogen atom? In the case of the hydrogen atom, you know the non-relativistic eigenvalues of the form minus a half mc squared alpha squared over n squared, m the mass of the electron, alpha the fine structure constant 1 over 137, and n an integer 1, 2, 3, and so forth. So these things go from minus 13.6 electron volts to 0. But we're leaving out the continuum states where the electron has enough energy to leave the proton, and those continuum states have are essentially, the energy of them, of each one, is essentially p squared over 2m, where p is the momentum of the electron at infinity when it's been ionized, when the hydrogen atom has been ionized. Now, the completeness proof, it's a pity we don't have aren't able to use the computer the way we were in the old building. What we can do is we can generalize the energy function a little bit and define it this way, namely an integral from A to B of Pf G prime prime minus, well, no, I'm sorry, I skipped a line. It's P F prime G prime plus Q fg dx, that's E, and then n of f and g is an integral rho fg dx, again from A to B. So these are slight generalizations of E of u and n of u. And what one can show is that this is actually just an integral from A to B of FLG dx. Again, we were able to throw away the boundary terms because we're assuming that f and g are in the domain. And so now we're going to look at the eigenfunctions uk with eigenvalues lambda k, weight function rho uk. And we're going to expand f. We're going to approximate it by a sum of the first n of these eigenfunctions. Suitable function ck, suitable coefficient ck uk of x. And of course these ck's will be given by the formulas that we were just discussing, namely can be written as n of f comma uk, which is to say integral rho f uk dx from A to B. This piece of chalk is kind of falling apart. Nuts. All right, let me leave these equations down there, although if you have the book in front of you, you can see all these equations. What we want to show is that the remainder term, f of x, minus the sum ck uk of x, k equals 1 to n, we want to show that this goes to 0. And to begin with, we know that this remainder term is orthogonal to the first n eigenfunctions, because if you multiply the right-hand side by rho and by you say we'll call this UL. Multiplied by UL, integrate, and rho UL, integrate from A to B, this will give you C sub L, and this would be delta KL, and that would give you C sub L also. So the remainder term is orthogonal to the first n eigenvalues, eigenfunctions. And the next eigenfunction, u sub n plus 1, minimizes the ratio R, let us say R phi, which is E of phi phi over n of phi phi, over all phi that are orthogonal to the first n. So uk k equals 1 up to n. So the n plus first eigenfunction is the one that minimizes the ratio of energy to normalization for all functions that are orthogonal to the first k eigenfunctions. And the first k eigenfunctions are the ones that minimize this ratio absolutely. Then lambda 2 minimizes the ratio for over the space of functions that are orthogonal to u1, and then lambda 3, u3 minimizes the eigenfunctions, minimizes the ratio with respect to all functions that are orthogonal to u1 and u2, and so forth. It follows then that lambda n plus 1 is less than or equal to the remainder term Rn, which is E of Rn over n of Rn. Because this is the eigenvalue that minimizes this ratio with respect to functions, all functions that are orthogonal to the first n eigenfunctions. So, turning this relation around a little bit, we can say that the norm squared of this, which is to say n of Rn, this is what we want to show goes to 0 as n goes to infinity, that this is less than or equal to E of Rn over lambda n plus 1. So, we're essentially done, because we know that the lambdas go to infinity as n goes to infinity. So if E of Rn remains bounded, then the norm of the remainder term goes to 0. The norm of the remainder term being this thing is an integral rho Rn squared dx. Showing that this is bounded is not really hard. All you have to do is actually compute E of Rn. And so that is E of, and this is F minus the sum ck uk up to n with F minus sum n, let us say cl ul. Because that's what Rn is. Now, if you keep track of what all of these things are, you can show that this is actually E of ff, the function we're trying to expand, the energy of the function we're trying to expand, minus the sum lambda k ck squared. Well, these things are positive. Everything's real, so ck is real, so this is positive. The lambdas might start out negative, like in the case of the hydrogen atom, but eventually, since they go to infinity, they get to be positive. And so what you can see then is that this is less than or equal to E of ff. So now we see that this numerator is bounded, it's less than E of ff. And so we have then the relation that n of Rn is less than or equal to E of ff divided by lambda n plus 1, and that goes to 0 as n goes to infinity because the eigenvalues go to infinity. You may wonder, why am I going on and on about this? Why is this important? Well, it's important in quantum mechanics because the idea that we have is that the various, say, energy eigenstates of a system that we can use those energy eigenstates to represent an arbitrary state of the system. So we would write this as sum on n, some constant, let's use k, some constant ck, energy eigenstate uk, ek. And if we take the inner product of that with the position eigen, what is it? Bra. This is the equation. Psi of x is equal to a sum on k, ck. This would be the uk of x. So fundamental to quantum mechanics is the idea that these eigenfunctions, which are the energy eigenfunctions, can be used to represent an arbitrary wave function, because we're thinking of this as an arbitrary state of the system. It's an arbitrary wave function. So that's quite important in quantum mechanics. Mathematicians, of course, improve upon what I've been going through here, namely Courant, Hilbert, and Stackpole show that the eigenfunctions uk of x of any regular Sturm-Liouville system form a complete orthonormal set, in the sense that every function f of x that satisfies either Dirichlet or Neumann boundary conditions and has a continuous first and piecewise continuous second derivative may be expanded in a series, and the series is a series like this that converges absolutely and uniformly on the interval. So let's see, if we go back to this delta function formula up here, I used MATLAB, I think. Anyway, the code is, I put the codes of all these things on GitHub or GitHub, whatever it's called. So I right, so there's the delta function. So for the case of Bessel's system, the weight function is just x, so I wrote this as x, y to the 1 minus alpha, alpha being this alpha here that's between 0 and 1, sum uk for system n of x, uk system n of y, k equals 1 to infinity. So I actually, instead of doing infinity, I did 10,000 terms, and these UKN for this Bessel, the nth Bessel system, these are the suitably normalized ones, square root of 2, the nth cylindrical Bessel function of znkx divided by jn plus 1 of znk. And what you can see in figure 7.3, which unfortunately I can't display because the hardware in this new building sucks, you can see I did this for y equal to 0.47, alpha equal to 0, y equal to a half, alpha equal to half, y equal to 0.53, and alpha equal to 1. And you see these three delta functions. And the y-axis was minus 2,000 to plus 10,000. And the x-axis goes from 0.46 to 0.54, just to cover the region there. By the way, these ZNK yeah, is the zeros of the, this is the kth zero of the nth Bessel function. So in other words, Jn of Znk is equal to 0. A friend of mine told me that during the Second World War, the British government classified the zeros of the Bessel functions. And of course, that was before we had these inexpensive computers that can almost instantly compute the zeros of the Bessel function to greater accuracy than the British government was able to in the early 1940s. This friend of mine, I think his father was in the British Navy during World War II. So let me now, let's see, where do we have blackboard space? I think I'm going to go to that, or maybe I should just go to this blackboard here. First are these inequalities of Bessel and Schwarz. I think, well, let me just write them down. Rho of x, absolute value of f of x minus sum k equals 1 to n aka k of x. Obviously, this is greater than or equal to 0, and if you now remember what the formula for the coefficients is, then you get one of Bessel's inequalities, integral from a to b, rho of x, absolute value of f of x squared dx greater than or equal to sum k plus 1 to infinity of ak squared. In fact, in general, you get an equality here. The arguments we use to derive the Schwarz inequality in Chapter 1 give us another inequality, integral a to b, rho of x, f of x squared dx, times integral a to b, rho of x, g of x, absolute value squared dx. Maybe I should have used y here. Anyway, greater than or equal to absolute value of the integral a to b, rho of x. Here these typically are real functions, but one can imagine they're complex. So this is basically the absolute value squared of the inner product of f with g, and this is f squared, g squared. In Dirac's notation, this would be ff gg greater than or equal to gf absolute value squared, which of course is just gf f g. Okay, let's see, what is the time at the moment? Okay, we only have 15 minutes left, and I want to get to, well, I don't have that much to do, so maybe it's not so bad. Just something about Green's functions. We learned a lot about Green's functions when we were talking about Fourier series and Fourier transforms. So I'm going to abbreviate this. The Green's function in this case is g of x is delta q of x. that way we can solve for an electrostatic solution. It's an integral g of, let us say, x minus y, rho of t and y over epsilon 0 dqy. And this basically is Poisson's equation. And the actual Green's function, g of x minus y, is an integral e to the I x minus y dot k over k squared dqk over 2 pi cubed. The reason this works is that when the Laplacian hits the Green's function, it brings down ik twice, which is minus k squared. The k squareds cancel, the minus signs cancel. You're left with an integral e to the I x minus y dot k dqk over 2 pi. That's delta of the delta function of x minus y. Similar Green's functions. I'm basically repeating stuff that we learned in the section in the Helmholtz Green's function. This GH, I think we solved this for this in the chapter on complex variable theory. It's e to the I m r over 4 pi r. For the modified Helmholtz equation, plus m squared there, gmh of x equals delta cubed of x. The solution is the Yukawa potential. Gmh of x is e to the minus mr over 4 pi r. Here in both cases, r is just the length of the vector x. The Green's function for the most famous Green's function is 1 over 4 pi r, and that in fact is this Green's function. This is a Fourier representation of the same Green's function. Another way of writing this is 1 over 4 pi, let us say x minus y. This is then a double sum. L equals 0 to infinity, sum m equals minus L to L, 1 over 2L plus 1, R lesser to the L over R greater to the L plus 1, YLM theta and phi, Y star LM theta prime, P prime. Here the prime coordinates refer to the angular, refer to Y and the others to X, or vice versa. And so one can use this Green's function, substitute in here, and what you get is a what's called a multipole expansion, namely phi of t and x is the sum 1 over 2L plus 1, 1 over R to the L plus 1, sum m equals minus L to L, QLM, Y, LM of theta phi, where QLM is an integral of R, Y, R to the L, Y, LM complex conjugate, theta phi, rho of t, and x, electric constant, dq this is the multiple expansion. You've probably seen it in the course of electrodynamics. If not, some faculty member may torture you with it next semester. Okay, let's see. Well, I guess we have enough time to compute a couple of these things. Well, the Feynman's propagator, let me just mention this. This is another Green's function. It's an integral e4th q. Now it's over to pi to the 4th EI qx over q squared plus m squared minus I epsilon. This minus I epsilon is Feynman making use of that trick, that principal part trick. What's the French name associated with that? Cauchy's principal part. All right, anyway, doesn't matter. The differential equation is m squared minus box delta f of x, which is m squared plus d by dt squared minus Laplacian on the Feynman propagator is the 4-dimensional delta function. And here qx is q dot x minus q0 x0 typically being time. Another property of, another way of thinking about Green's functions is, for example, if we think about this delta function. In fact, here I'm just in one dimension, dk over 2 pi into the ik x minus y. This delta function is being written in terms of the products of eigenfunctions of the differential equation minus d by dx squared plus m squared with eigenvalues a squared plus m squared. Or I could have left m squared out and just talked about minus d by dx squared and a squared. So we can, of course, generalize that, and we can imagine we have an arbitrary one-dimensional Storm-Liouville. I switched from n to k without realizing it. Equation like that. The eigenfunctions are orthogonal. Oh, there's a typo. Hold on. So if this is NL, this is L, and this is integral rho UN UL dx. These are orthogonal. And so what we want to find is a Green's function, g of x minus y, that gives us delta of x minus y. And what we can do is we can say, well, let g of x minus y equal the sum on k of uk of x, uk of y, divided by the kth eigenvalue, lambda k. And then if L hits g of x minus y, what we get is a sum on k, L uk of x, uk of y. lambda k, but LUK is lambda k rho UK of x, UK of y. We have a lambda k here. And so what we're left with then is a sum on k, rho of, it's actually rho of x in this case, UK of x, UK of y. Well, this is what we expect to be the delta function, as we verified many times. And so that's another way of thinking about delta functions. Namely, you sum over the eigenvalues, product of eigenfunctions. That's one dimension. You might wonder, well, why is this an integral instead of a sum? Well, it's that the eigenvalues of d by dx squared are continuous. Their k is any real number. And so you have to integrate over them as opposed to summing over them. I think I'd like to skip the next section. I never liked the problem in the next section, so I'm going to skip it. What is the time situation? Are we out of time? And if not, I think maybe we should talk about questions. We've got a few minutes left. Somebody might have a question. Remember, I've got candy. I have 3 candies left, so I can pay for 3 questions. Is anybody starting? Well, why don't you turn the camera around so that it's on me, I guess. So no questions? All right. The next topic is symmetries and conserved quantities in field theory. This is is the field theory generalization of symmetries and conserved quantities in mechanics that we went through earlier in the course. And the key insight here was developed by Emmy Noether, who was a German mathematician who emigrated to the United States, and I think she taught at one of the Ivy League girls' schools in Pennsylvania. I'm not sure. In any event, what we'll be talking about is cases where the Lagrangian doesn't change when one makes some sort of a change in the fields. So this normally is a partial of the Lagrangian with respect to a given field, a change in the field, plus the derivative of Lagrangian with respect to, let us say, the alpha derivative of the field. By the alpha of the field times the change in the alpha derivative. So we're imagining that we have a symmetry in that this change in the Lagrange density actually is 0. And what we'll see is that this means that there's a current, namely JA, which is a sum on I, partial L with respect to dA of phi I times the change in phi I. This current is conserved. And by conserved, I mean dA, JA is equal to 0. And so this is J0 dot plus the divergence of J and up to 0. All right, I think we're basically out of time exactly now. So, all right, let's turn the camera off.